Oui. Ouais. Should I cut my... Ok. Tu peux nous remontrer.
The camera's too high.
No, that's good.
It was on purpose.
Okay. Okay, hello everyone. This is the second hangout of this gravity course, and hello to everybody who is outside the course but wants to follow this hangout, which is on the occasion of a very special event, the centenary of general relativity. In 1915, in the month of November, Einstein wrote 4 articles in a row. Each of them was, by a week later, and the last was published on November 25. And so we are here to celebrate this, to try to understand better general relativity, and we are here with great experts on several aspects of the theory. Let me first start by telling you a little about the place where we are. You have seen this is not your standard laboratory. This is the Paris Observatory. And so let me first ask Derek Liss, who is representing the president of the Paris Observatory. Could you tell us in which place we are?
Well, good evening, or perhaps good morning, depending on where you are. I am a director of LERMA, one of the scientific departments of Paris Observatory, and on behalf of President Claude Catala, I would like to welcome you to the council room in the historic Perrault building here in central Paris. Paris Observatory is one of the largest astronomical centers in the world. It is also the oldest astronomical observatory still in operation today. It was founded in 1667 by Louis XIV, the Sun King, whose portrait is hanging on the wall behind us. The Paris meridian was defined as passing through the center of the Cassini room upstairs. A number of great astronomers have worked here over the years, including the Cassini family, Christian Huygens, who invented the pendulum clock, Olof Romer, who measured for the first time the speed of light, or Jean Picard, who measured for the first time with high accuracy the size of the Earth. When the metric decimal system was introduced, the kilogram and the meter standards were kept building for a hundred. Today, most of French astronomers work on all aspects of modern astronomy, including of course, cosmology, gravitation. So I'm delighted thanks to the progress of modern technology and us in this historic symbolic location.
Okay. Well, thank you very much. So you have seen we're trying to see that sometimes we are. Probably we ask Thomas to use his microphone. Probably that's what takes us to for the time being, because this system is reacting to sound. Okay. Now let's get back to Einstein, and maybe George, you have something to say about that person that you saw, some things that you saw at the beginning there, and Luc, astronomer, Le Verrier is very well connected to Einstein.
First, let me say, I'm wearing my Einstein. Unfortunately, it's a special topic. I had to choose.
Mute your microphone, so not in use.
Activity tie. So for the university, I'm wearing the ties I have. And he's certainly here. But his work on a lot of observations, and a lot of other things. And one of the things that's very interesting, this person just Louis XIV, Leverrier, he was a astronomer working here and eventually head of the observatory. His early work was measuring the planets and their behavior and seeing if they followed Newton's laws around the sun. And when he was studying very carefully the orbits of Uranus, he noticed it was slightly off from what it should be, and he calculated the perturbations could be caused by another planet, which eventually became discovered as Neptune. And so by simply using Newton's laws, advanced mathematical techniques, and a pencil, right, he was able, in the old observations, he was able to discover a planet, although he had to write to his friend at the Berlin Observatory and had him look for it, and it was within a degree of where he predicted it. And that was back in 1846. But as part of that program that he carried on, he made more and more precise things. And he got to be a hero of mine because I'm from an era in which we had to take mathematics courses that dated from before computers. And so we had to learn all these techniques for doing approximations and higher order terms and so forth. He carried out 7th order terms for measuring the orbits of all the planets. And he discovered that there was a 10% error in the advance of the orbit of Mercury around the sun. And this missed is 43 seconds of arc per century, a really tiny amount. An arc is a 60th of a minute, which is a 60th of a degree. So a very tiny, small amount per century. And yet he was so careful with his calculations and the observations, he was convinced that there was an error there. And people thought, well, maybe it could be another planet inside of Mercury, or it could be a oblate sun. But when Einstein first was publishing his general theory of relativity, he predicted the 43 seconds of arc per century as a consequence of general relativity. And that made people take the theory more seriously, and is eventually followed up by Eddington going to do measuring the bending of light by the sun in 1919. So Leverrier impressed me in doing his math. He impressed me that not only did he show Newton was right, but he showed there was a correction to Newton, which led us to take on general relativity.
Okay, so let us introduce. You have, who is at the Paris Observatory. So let us introduce our guest, and I'll probably first ask myself a question. I'm probably not entitled to, because we have lots of questions to answer on your behalf, but. Let me take advantage that I have a microphone to ask a question to each of our guests. What do they think is sort of important today in general relativity? We'll talk later about the next 100 years, but at this point, what is why is general relativity so important? And so let me first maybe ask. Gaby Gonzalez was professor at Louisiana State University, and she's the spokesperson of LIGO Science Collaboration. So probably that means that since I'm convinced that LIGO will discover gravitational waves, LIGO and Virgo will discover gravitational waves, she will be the person to announce it to the world. So for the time being, Gaby, could you tell us what you think is sort of important nowadays regarding general relativity?
Well, first of all, let me thank you for inviting me to be here. I think this is great, and it's a very exciting day.
Gaby, we don't get the sound.
Can you not hear me? I have my microphone open now. No?
Okay. I can hear Gaby.
Hello? Carsten, you can hear me?
Go ahead.
Yes, I can hear you.
We had the volume turned down here, so we wouldn't hear ourselves.
Yeah, we dropped the sound on our side. I was just saying before we start saying that this is much more difficult. Okay.
Okay. I don't think this is Okay. So let me say again that, first of all, thank you for inviting me. I think this is a great hangout and a great day to do it, of course. To me, the theory, of course, is beautiful, but what's most important is that it doesn't only predict effects that are very difficult to measure, like gravitational waves, and those we hope to measure soon, but it predicts this interaction between space and time. It predicts how light bends in space-time, and all of these, now we think, in the beginning, the effects were so small that Einstein himself thought they were unmeasurable. The light bending was so difficult, and that was the first one to be measured. But then later on, the light bending and the effects of gravity on the timing of clocks is something that now we use in GPS. So effects that were so small in the beginning now are practical and very important for our daily lives. Without GPS, I would get lost every few hours. Gravitational waves are, of course, the most exciting effect that I think we are going to measure very soon, and we have been involved in this for decades. We know they exist, so we are very safe about the prediction. It's the measurement what is so difficult, and what's so, because it's difficult, it's exciting, and that is what inspires me the most at this time.
Okay, well, thank you. So let's go through, the four of you. Carsten Dantzmann. Carsten is director at the Max Planck Institute in Hanover, and I think this is good for today's purpose. This is called the Albert Einstein Institute. And Carsten is leading the European effort for a space mission, the ELISA mission of the European Space Agency. So we don't have the image of Carsten, but we have the sound, and we have his portrait next to Einstein. So Carsten, so what do you think is sort of the topical in general relativity these days?
Good afternoon, Pierre, and good afternoon to all the other ones out there, the hundreds or thousands, I don't know how many are looking, or maybe a dozen. I'm sorry that my camera isn't working. It just broke down minutes before the transmission, but you have a picture of Einstein. That's actually much better and very fitting. And in front of Einstein, that's me a few years ago. It's an exciting time for general relativity. So it's now 100 years, and it's interesting to see that for a large fraction of those 100 years, general relativists were safe. They could just predict anything, and they didn't have to be afraid that there would be an experiment that actually checks what they were predicting. This has now profoundly changed, and general relativity is now moving into mainstream experimental science. And that is what I find so particularly exciting. And also, I find this particularly exciting because I've spent most of my active scientific life chasing for gravitational waves experimentally, and we are now so close. That'll be an interesting astronomy that we have to see developing over the next couple of years.
Okay, well, thank you, Carsten. Now, let us ask the same question to Roger Blanford. So Roger is a professor at Stanford, the former director of a big institute at Stanford, and he is a world expert in many things that have to do with general relativity, especially black holes. We'll see in the course black holes next week, but so he has, but he's also an expert in many other aspects of high energy astrophysics and so on. So what's your point of view on that question, Roger?
Bonsoir, Pierre. Hey, tout le monde. Thank you very much for inviting me. I think this is a very exciting time in general relativity. It has passed all of the tests that have been laid in front of it with flying colors due to exquisite experimental science. It is now on the cusp, I think, of moving into three quite new directions. The first of these is to test general relativity when you're dealing with very deep gravitational potential wells, most famously of all a black hole. And after Carsten and Gabby make their first detections of gravitational radiation, they have the opportunity perhaps of discovering a black hole system, and that will be a wonderful new, qualitatively new test of general relativity. The second new direction is in cosmology, and there we're looking at the universe at large, and it is by no means guaranteed that general relativity, as developed by Albert Einstein 100 years ago, including the famous cosmological constant, there's no guarantee that describes the universe on the largest scale, and measurements in cosmology over the past 15 years and likely over the next 15 years are going to probably answer that question conclusively. So far, we see no reason for departing from what Albert Einstein told us. And then thirdly, and this is perhaps the most exciting of all, is the impending marriage of quantum mechanics and particle physics with general relativity. We do not know if this marriage will be consummated, but many people are trying to take general relativity into a direction that Einstein himself put a lot of effort into, but was, I think it's fair to say, unsuccessful. We are trying to do this in a somewhat different ways today, and I'm sure Thomas will have more to say about this.
Okay, well, thank you. So indeed, let's move to Thomas Hertog, who is professor at Leuven University and who is a theorist working on string field. Thomas.
Hi, good evening, everyone. Thanks for joining us. Yes, so this is indeed a wonderful day for general relativity. Einstein equation really governs the universe as far as we know, and some say it is it is perhaps the most beautiful theory ever written down. And in fact, I'm in Leuven in Belgium right now, which is the place where a Belgian priest and cosmologist, Georges Lemaitre, first started to apply Einstein's theory to the entire universe and predicted its expansion. And as Roger said already, it is through its application of the theory to cosmology and to the workings of black holes that we hope to not only learn more about general relativity, test the theory in new domains, but also explore its limitations. And I'm personally most excited in the coming years to really get a handle on how far we can push general relativity and where exactly it's going to fail. Because Einstein's theory, in a sense, predicts its own destruction. It predicts its own failure deep inside black holes, and right at the beginning of time, at the origin of our universe. We have very good evidence now that Einstein's theory ceases to be correct. And one of the key open questions is what and how what replaces it, and how the unification, as Roger said, with quantum theory will work out. Thank you.
Okay. Thank you very much. I hear myself twice. I hope that everybody else does. Okay. Just a second. Someone is making fun of us with this. So much trouble. I have a problem with it. Okay, so let me start with the first question. Do I get Thomas, could you switch off your microphone? Okay, so yeah, if anybody is on, then we get an echo. Okay, so let us start with a first question, which was asked, some time ago on the FutureLearn platform, and that's from Cameron. was asking, I've heard it said that Einstein turned gravity into geometry. Could you expand on this connection? Who wants to answer this one? Nobody wants. Roger?
Oh, well, I'll try. I think Einstein was always, from a child, fascinated by geometry and the tales of him discovering Euclid's geometry, for example. And his first theory of relativity, the special theory, did not, in the way he presented it, have much to do with geometry. But then the linkage slowly became to appear, partly from the work of Minkowski, and then by the time of 1915, it was abundantly clear to Einstein that he had to master the mathematics of more general geometries than that of Euclid. And he did this. He was not a natural mathematician, but obviously a very competent one, and he learned the geometry that was developed by Georges Riemann and developed by others in the 19th century, and then realized that this was the way to generalize his special relativity and create the general theory. And the general theory is encapsulated, if you like, in an equation, and that equation in words says that the curvature of space-time is given by the amount of material in that space-time in a way that can be quantified and calculated. And the other aspect of geometry is that bodies like planets will follow what are the functional equivalents of straight lines in that curved space-time. So geometry is very central to general relativity, and Einstein realized this, and 100 years ago was the culmination of a huge intellectual effort to bring this into being.
Thank you, Roger. So maybe to follow, let me select one question by Alana. I should actually tell everyone that if you want to ask questions directly, you can use the Q&A, and if you're following us on Google Hangout, then you can use the Q&A and ask questions directly. So let me select one of these questions, which is, okay, here it is. If you have this app on, does the curvature of space-time replace the gravity force? Does an apple fall on the Earth because of the curvature of space-time? Who wants to answer this one?
Yeah, the answer is yes, of course. Newton talked about a gravitational force, but it was never clear what that force was. What was the mechanism behind Newton's universal force of gravity? One way of phrasing Einstein's search is as a search for an answer to that question. What is the mechanism behind gravity? And his answer in 1915 was, there is no force. There is nothing that pulls, but it's the curvature of space-time itself which we experience as gravity. So it's all pure geometry. That's all it is.
Very well.
Very well.
So good. Yeah, thanks. So now let us. We have some questions about test of relativity, and there is one. So we might discuss that a little, because of course this is important. That this theory has been tested a lot from the first days, and so far as we some of us have said, this has been each time verified. But there is a question of test of general relativity in the strong field regime. And for example, we have one from Philip who is asking, is strong field tests like pulsar orbiting around a black hole lead to inconsistencies? Where do we go from here for the theory of gravity? So maybe Roger, you can answer this one. because you're an expert on you know, what happens very close to black holes and so on.
Right. I think following the gas that orbits a black hole is a very exciting thing to do, and of course it is something that is accessible, especially to X-ray telescopes and increasingly to radio telescopes. And one of the exciting observational developments that we await is the ability to start to almost image the black hole at the center of our galaxy and in a nearby galaxy called M87 using sub-millimeter, very long baseline interferometry. That means using radio telescopes in different continents and being able to start making a crude image of the gas following the black hole, so orbiting the black hole. So this is a very real possibility. Now, the trouble is that if we look at that gas, we're stuck not with the 20th century physics of general relativity and quantum mechanics and so on. It is the 19th century physics of gas dynamics and electromagnetism that will confound us. And it will be rather hard to make a case from those observations that says Einstein was wrong, it does not describe what we see. It's possible, but I think now rather unlikely. What we will be able to do is to interpret those observations, assuming that general relativity is correct. For me, the gold standard of testing whether the strong field version of general relativity is correct is what I hope Gabby and Carsten and their many colleagues will deliver eventually, which is an observation of the coalescence or merger of two black holes. And there we can study the waveforms, and there I think it is possible to imagine a test that would refute the detailed predictions of general relativity. And I'd be very interested to hear what they have to say about that.
Okay, so maybe, you know, either Gabby or Carsten want to sort of take the lead now, as you were asking.
I think that's the one that Gabby should take.
Mm-hmm.
Okay, yes. Yes, of course, we probably, at least I, even as a child, was curious about black holes. So black holes is what we really want to detect, because it will show us, like Roger said, this geometry being bent in very strong fields near very, very high masses. We will probably see coalescences. We hope to see coalescences of many different systems: neutron stars and black holes, and two black holes, the small black holes, not the big black holes at the center of the galaxy, but smaller ones of few to tens to hundreds of solar masses. And if we happen to have a coalescence of two of these black holes, then, like Thomas said, it's pure geometry. We have masses, but the masses are inside the black hole. So we are going to be looking at the signal produced by pure geometry traveling over millions of years to arrive here to us. So that is very, very exciting. It's not the only thing we hope to see. Like I said, we also are looking at and probably more hopeful in detecting larger numbers of neutron stars and black holes. But we don't know. We'll take whatever nature throws at us. But black holes is probably the most exciting event we're expecting. Yeah.
Maybe I can add to that. Yeah, black holes are certainly very exciting. That has always struck me as mind-blowing, the inherent nonlinearity of the field equations, and that you can think about a world that only consists of curvature and recreates itself. By the time we go into space, of course, we can see the other side of the black holes, the really big ones, the supermassive ones, like the one that we have in our own galaxy. And then with a space detector like LISA flying, we will do precision measurements of space-time curvature, in particular when we see little things falling into big things. And it takes 100 years and traces out in fantastic accuracy the structure of space-time, and it is so precise that it lets us look for minute variations from simple relativity. Any type of strange field or new particle that we're talking about might show up in these detections. Okay, we'll have to wait a few years, but it will happen. someday we will look at gravitational wave astronomy over all frequencies, just like visible astronomy, which goes from far infrared and radio waves to X-rays and gamma rays, and so it will be with gravitational waves. We will see them at frequencies from 1 over the age of the universe all the way up to many kilohertz. That'll be an exciting time.
But precisely, for example, Magdalena is asking us this question: why is it so important to detect gravitational waves? Why do we get more information by detecting gravitational wave than light or electromagnetic waves?
Well, if I can jump on that too. Of course, when two black holes, especially of the kind that LIGO and Virgo are looking for, these smaller black holes, are not necessarily expected to produce light waves, electromagnetic waves, unless there is, of course, gas and other material around. But the black holes themselves, the collision of the black holes themselves, will not produce electromagnetic waves. It will produce gravitational waves. And not only that, but those gravitational waves are going to travel through space to reach us without being distorted at all, almost at all. So they travel through dust, they travel through galaxies, through dark matter, everything with the pristine information, carrying a pristine information about the source. So we will be learning about those sources with very, very good, uncorrupted information, which is different, complementary than the information we get from electromagnetic waves. So I think detecting gravitational waves is not important because it's a test of Einstein's theory or because it's of course, those are all exciting things. It's a bending of geometry. It's also important because it will let us see these sources, not just, again, not the black holes, but those are the ones we can, we get much more information than from electromagnetic waves, but from neutron stars, which do produce electromagnetic waves, and then we will put the two pieces of the puzzle together to learn more. So it's a completely new window, which I think it's a phrase we have used very often, but it's very true.
Maybe I can add to that. We should be aware of the fact that the universe is dark. Almost all of it is dark. 99.6% of the universe are dark. 70% is dark energy, where we don't know much more than the name. 25% is dark matter, where we know a little bit more, but also not much more. But even of the 4% matter as we know it, only 10% really is bright and emits visible light. So almost all of the universe is dark, and pretty much all we know about it is everything interacts via gravity. And everything that interacts with gravity and forms structure will emit gravitational waves. So that is the remote hope that gravitational wave astronomy will let us listen to the dark side of the universe. And that's what's really driving me in the dark hours of the day.
Okay, now we know what is driving you. Well, precisely, we have a question from both Salma and Kathy, who are asking, sort of following the trend that you were taking, regarding gravitational waves. What effect does dark energy have on them? Who wants to answer that one? that's a difficult one.
Well,
Thomas going to take it?
Either way is fine.
Okay, whoever.
Okay. Dark energy.
Thomas, go ahead.
Yeah. So the question was about dark energy, right? And its affection, how it affects gravitational waves.
Yes.
Well, dark energy, as Carsten just said, makes up 70% of the energy content of the universe. And therefore, it has a huge impact on the geometry of the universe through Einstein's equation, through Einstein's theory. So when gravitational waves reach us from the distant corners of our universe, those gravitational waves have traveled through the geometry of the universe for eons and eons, sometimes for billions of years. the pattern that we will observe of those gravitational waves will therefore be affected by the geometry of the universe, and thereby provides an indirect measurement also of that geometry. So when gravitational wave astronomy gets going in a few decades, we will be able to use gravitational wave patterns that we observe to independently measure and probe, in fact, the underlying geometry of the universe, potentially all the way back to the Big Bang. Because after all, these gravitational waves just travel uninhibited through the entire universe.
Can I just add to that a moment?
Yeah, absolutely. Please.
I think, as Thomas just said, the expectation is that the only influence of dark energy, or equivalent the cosmological constant, as far as we know, on gravitational wave is through the geometrical route, the way it changes the geometry of the universe at large. However, as we can't identify the physical nature of the cosmological constant, there is always the exciting, if remote, possibility that there is a more direct interaction rather than the purely geometrical one. And this is one example of the discovery space that is out there for the second century of general relativity to confront.
Yes, we'll come to that indeed, which is the future of of general relativity. So I think we have sort of answered the question of Pamela, who was asking what information will gravitational wave provide about the origin of the universe. Let me come back a second. We have a very popular question which seems to appear several times. So let's come back to Einstein, and Dominic and many others are asking the following question. Why was Einstein such a believer in the static universe? It was the reason why he introduced the cosmological constant. So why did he believe that the universe was static? Who wants to take this one?
All right, I'll try.
Okay,
so
George.
You can't know for sure, except for what he said and told us, but it was a common belief in those days that the stars are unchanging. And just have your own experience. You go out night after night and the sky looks the same. On a human time scale, the sky doesn't change. The stars stay pretty much in their own position. We've had to build tremendously powerful and very good satellites to go up and measure the location of stars so precisely that we can see this low drift in the sky. So if you look out and you see night after night with your own eyes, the stars are not changing, it's hard to imagine that the universe is changing so much. And so I think he just fell into the common belief that everyone had in those days, that the universe was static just because it seems static. Now we know we have to look on a much longer time scale than the human time scale or human civilization time scale, and then we see changes, just like geology changes.
Can I possibly just add something to that?
Yes.
It is often said that the introduction of the cosmological constant was Einstein thought it was his greatest blunder and so on. Of course, we now know it wasn't. But I think we should recognize that the additional understanding that adding this term called lambda, or the cosmological constant, to his field equations was something that was really possible and very appealing, was a truly remarkable insight. And the fact that he didn't take the next step and solve the equations for an expanding universe, as De Sitter, Friedman, and famously Lemaitre actually did, should not be held against him, because the first step of recognizing that his equations could be augmented in the way that they were to allow this possibility of the cosmological constant, which has led now to an interpretation of the accelerating universe, was a truly remarkable insight, I think, even in the context of the development of the general theory of relativity.
Okay, thank you. So maybe let us come back to gravitational waves and everyday life. Kathy is asking a question. Is there a practical use of gravitational waves possible, like in science fiction? So either Gabby or Carsten, you have to answer that one.
Well, I have to say that at this time, we don't imagine everyday use of gravitational waves instead. So of course, the technology that has been created to detect these gravitational waves has a lot of spin-offs in other industries. But that doesn't mean that they're not going to be important decades or in the even near future. When Einstein created his theory, he never thought it would be important for daily life, and as we know now, we have to do that for, like I said, we have to use that for getting a good GPS localization. If not, we get it very wrong. So that becomes now something that we use in daily life. We can never predict the future. The laser, when it was invented, it was thought. I think somebody said it was a solution looking for a problem, because what could it possibly be used for? And we can't imagine our life now without lasers. So no, I don't think that I personally, perhaps I'm limited in my imagination, but I don't think I cannot imagine using gravitational waves in daily life, perhaps in the next decade, perhaps in my lifetime. But I don't discount that they will be very important for daily life in the future.
Okay, so maybe you're hiding something from us, because David is asking a question. Yeah, let me read it. So the question is a little more general than the previous one. He's asking, can interferometers do any kinds of science while they are out there? So he's asking, for example, detecting faint black asteroids passing by, listen to solar winds. But then he adds, and that's, I would like to get your opinion on that. He heard that LIGO was detecting the sounds of crickets. So is there any truth to that, or can you tell us about that?
We are the LIGO detectors are very, very sensitive to lots and lots of different noises. I don't think we are sensitive to cricket noise, but we are sensitive to ocean waves, to the seismic noise produced by ocean waves farther away, to electric storms farther away, to earthquakes, relatively small earthquakes on the other side of the Earth. So you could say that this is an instrument that measures those things, but because we have designed the instrument to be as insensitive as possible to those effects, then it's not really a good instrument to measure those effects. We can use seismometers to measure seismic noise. We can use microphones to measure acoustic noise, and those are much better instruments. Our instruments are designed to be as insensitive as possible to those noises. We are not perfect, so we are still sensitive, but we are not good microphones for cricket noise, no.
Okay, disappointing. Okay, so let's move on. We have one question from Chaitanya. We're discussing cosmological constant, and we have also discussed in the course dark energy. So the question is there a difference between Einstein's cosmological constant and dark energy? Who wants to answer this one?
Okay. Should I try that?
Yes, absolutely. Yes, absolutely.
Okay. The original idea of Einstein was to introduce this one term, sometimes called lambda, in the equations to describe cosmology. And this was just a single number that was universal, it was eternal and ubiquitous. We saw it everywhere, and it led to a very simple solution of the equations, if you like, a very simple description of cosmology. And so far as we know, that suffices to describe the large-scale expansion of the universe, but we don't know that for sure. In recent years, as physicists have thought more and more about the nature of that cosmological constant, they have come increasingly to associate it with a quantum mechanical phenomenon, which is called the vacuum. And this is sort of the marriage, if you like, with quantum mechanics. And that has been a big puzzle, I think, for physicists, and they have therefore thought about generalizations of the simple cosmological constant idea, and those nowadays I think are largely called dark energy, although there are other words that are used. And these are, if you like, richer theories that would describe the large-scale structure of the universe, and much of the measurement in contemporary observational cosmology is directed towards seeing if those richer theories are needed or whether the simple idea of the cosmological constant suffices.
Well, I think time will. Oh, Thomas, you wanted to.
Maybe I wanted to add a little note on this. So the interpretation of the cosmological constant as energy associated with a vacuum goes in fact back many years already, and it raises another puzzle, which has to do precisely with the marriage between general relativity and quantum theory. And the puzzle is that in a typical quantum theory, the energy of the vacuum is a lot larger than the value of the cosmological constant that we observe. You might wonder, well, what is the problem? The problem is that it raises an interesting puzzle as why was this value of the cosmological constant that seems to be the right one in our universe, why is it so incredibly small? And this is in fact that observation, that cosmological observation, is in fact one of the few, let's say, one of the few observations we have to guide us in bridging or combining Einstein's theory with quantum theory.
So indeed,
I could add some more.
Okay, let us have George.
Those. Speak loud. Okay, the discussions you heard were basically talking about coming from the cosmological constant to thinking about the vacuum energy and thinking about what would cause it. There are a set of theorists or phenomenologists who just try and describe the phenomena, and they think there's some new material, some new fluid, or some new substance that is added, and it has unusual properties compared to ordinary matter and radiation in that it's dominated by the potential. It's very similar in some ways to the Higgs field that fills space and gives the particles masses. And so people have made up this kind of phenomenology and theories, approximate calculations, to say, what if we just add this new kind of substance to the universe? Can we get the accelerating expansion of the universe? And the answer is you can. And it's even related to what we call inflation, those similar kind of theories. And so we cast a very wide generic net when we say dark energy. We can mean the cosmological constant, we can mean vacuum energy, we can mean some new substance, we can mean some modification of general relativity. So dark energy means just don't assume it's a cosmological constant. Let's see what it might be.
Yeah, so precisely, since we are talking about this sort of unified theory that would encompass quantum physics and gravitation, there is of course the question of a Big Bang. And so let me find again, we had one question about that from Alan, who was asking, what do you think of the chances of discovering, or at least developing, a theory of what was there before the Big Bang? And of course, that's connected with what we just said. So maybe Thomas, you want to answer this one?
Well, okay, I'll try. Well, first of all, at least according to Einstein in general relativity, there is no notion of before the Big Bang. This is really not on the table. In Einstein's theory, in general relativity, time literally comes to an end at the Big Bang. So the Big Bang you should view as a kind of emergence of notions of space and time. So when we're talking about theories of the Big Bang, we can't just be talking about general relativity, because general relativity is a theory that describes the evolution of a space-time or the geometry of an existing space-time. It does not describe the emergence of a space-time. So we will have to go beyond general relativity. And there are various ideas on this, but they're not fully developed, and there's lots of speculation and searching for, in the first place, a consistent mathematical framework that on the one hand contains general relativity, and on the other hand is consistent with our best microscopic theories, quantum theories of fields and all that. Now you might think, well, what are we hoping? Sorry.
No, go ahead.
Go ahead. What are we hoping to get out of such theories? Well, we're hoping to get out predictions for observations in our universe, such as the value of the cosmological constant, which we discussed already, or the pattern of microwave background fluctuations, which we see which are remnants, so to speak, of the radiation of the early universe. Those are all predictions which have something to do with the Big Bang, and therefore with the marriage of general relativity and quantum theory. So this is not just an academic exercise. The Big Bang is in a way right in our face. It's shining at us from all directions. But we won't be able to solve this problem just based on general relativity. Roger.
Roger, you want to add something?
Can I perhaps add something?
Yes.
About, as you mentioned, Pierre, there is a theory called inflation, which was introduced by Alan Guth and Andre Linde and many others, now quite a long time ago, that was devised to explain some otherwise puzzling aspects of the simple description of cosmology. And it provided a very appealing expression of ways to do this, and it furthermore had in its most simple form a set of predictions which appear to have been borne out by direct observational tests, especially those observations involving the microwave background radiation. The most exciting possibility, and here the predictions are not precise, but they are certainly there's certainly an expectation, is that a special type of pattern of microwave background polarization observations called colloquially B modes can be seen on the sky. Recently there was a claim that these had been detected, and if that had been the case, we would have been looking not just at the time of the microwave background photons, but at the very earliest instance of the universe. We now believe that those measurements that were made were actually produced by dust in our galaxy, but it is still possible that sometime in the future a more sensitive microwave background could remove this foreground dust and see the signals that have come all the way directly from the Big Bang, from the very earliest instance of the universe, almost the Big Bang itself. This is a very exciting prospect, and we'll have to see if the telescopes are good enough to do this and the universe cooperates.
Well, thank you. So precisely we are someone Thomas, yeah, thanks. So we started discussing the prospects. So let me ask Gabby and Carsten about the near-term prospects and maybe the very long-term prospects, the next 100 years of general relativity or the future theory. How do you see that?
Well, perhaps I can start with the next few years and Carsten can follow with the next decade. As you probably know, the advanced LIGO detectors, which is the second generation of interferometric gravitational wave detectors, are taking data. We have been taking data since September. We take data for about 3 months. We didn't have expectations of detecting gravitational waves because the detectors don't have the sensitivity that they can have, and we will be working to get the detectors at that sensitivity in the next few years. But we still haven't finished taking data, so we'll see what we have, and we'll tell you what we have when we finish. We do think that we have planned to take again data next year with detectors a bit more improved. We are now at a sensitivity that is 3 or 4 times better than the best we had with the first generation. We want to be 10 times better, so we are halfway to our design. But we will get there gradually, so we will be taking data again next year with better sensitivity, and with Virgo probably joining us, so we will have 3 detectors and be able to triangulate sources, and then again in the following year with even better 3 detectors, and in the future, so several years from now, we will have other detectors joining us. There's a Japanese detector in construction. There's a detector an observatory that will probably be built in India. So that will help a lot with the localization of the sources we have. So with the sensitivity that we expect to see tens of coalescences of neutron stars and black holes, at least. We don't know about black holes because we don't know where they are. We don't know how many there are. That there are large uncertainties because those are centers so large. We could be seeing them first or last. We don't know. But neutron stars and black holes and 2 neutron stars forming a black hole, which is very exciting. You're seeing a black hole being born. Those we know we're going to see many in the next few years, especially when we get close to LIGO design sensitivity and Virgo design sensitivity. But that's just the beginning. We know that we can improve the detectors if we have enough time, enough money, enough sources. But what I really expect is to really open the windows. This is going to be the first band in which we will see gravitational waves, but we know that pulsar timing techniques are looking for gravitational waves of much longer scale from supermassive black holes, and those are also a matter of time until we see them. LISA is guaranteed to see gravitational waves from coalescence of galaxies and black holes in galaxies, and those would be the best tests of general relativity because those would be the ones that have the highest signal to noise. So that's all coming up. That's the future. I don't know, Carsten, I think it would be good if you talk about Pathfinder. I think those are the most exciting news this year.
Yes.
Okay, I'll be happy to say something. First, let me tie directly into what Gabi says. We have to realize that until a few years ago, people thought there would be a fundamental limit to the sensitivity of gravitational wave detectors given by quantum mechanics to be reached soon. Now we know that is not true. For all practical purposes, there is no fundamental limit to the sensitivity of gravitational wave detectors. So the limit is just our own clumsiness in building the apparatus. And so I see a very bright future for gravitational wave astronomy as far as sensitivity is concerned. We will see more and more generations of ever-sensitive detectors covering the whole universe on the ground, and then a little bit later also in space and in all frequencies. So there'll be microhertz detectors, millihertz detectors, kilohertz detectors, and someday maybe even an improved microwave polarization experiment looking at the early universe. The space detectors are really coming along strong now. ESA has decided to fly a gravitational wave detector in 2034 as its L3 mission. And we are making the first step in 7 days, because in 7 days we have the launch scheduled for LISA Pathfinder. That's the precursor mission for the big LISA mission. All practical aspects, except the long arms of LISA, can be tested on LISA Pathfinder. The lasers, the interferometry, the optical bench technology, drag-free control. It's sitting on the launch pad in Kourou in French Guiana right now on top of a Vega, the new European small launcher. And as we talk, the fourth stage of the Vega is being fueled with unsymmetrical dimethyl hydrazine and nitrogen tetroxide. And those are things that are rocket fuel, and they're just as nasty as the names sound. And so basically the satellite is sitting on a huge pile of explosives that 7 days from now will burn, either slowly or very quickly, and of course we hope rather slowly. And then over the next 6 months, we will be seeing all the major things that we need for LISA coming into place. And then all we need to do is build 3 satellites and get the thing launched. And that takes a few more years, but it'll come.
Well, thanks, Carsten. So let me check, but can you hear me?
I can hear you. Yeah.
Okay, you can hear me. So because I cannot see myself, but
I can also see.
So okay, great. So it is now 1 hour since we started, so this is time to conclude. Well, first I would like to thank all of you. I think it has been very interesting, and this is an impressive panel of people who are really active in the field and playing a leading role. So thanks for taking the time to share your insights with us. I think I'm sure on behalf of all the learners of the gravity course, I would like to thank you. And I would like also to tell everyone that you see that we physicists, can also experiment, even theorists like me, and we are learning, and I think we've been improving over time. In this hour, it started a little in a hectic way, but I think we have been learning this tool. So we can also learn about how to deal with social networks and all that, not just, even though, as I said at the beginning, I think this is much more complicated than computation in general relativity. So we will have, Carsten mentioned the LISA Pathfinder mission. We will have our next hangout on Monday, live from Kourou, discussing with people from the project. So that should be also an interesting hangout. And we all will watch live, since you are all over the world. Some of you won't have to get up early. On December 2nd, it will be possible to watch live on the platform the launch of the LISA Pathfinder mission. So even though we are physicists, we cross our fingers and we expect the best for the mission and for the future of general relativity. And so let's now hope that in the next 100 years, we'll find the theory that replaces general relativity. Well, thank you all for joining us. And again, to all our panelists, thanks a lot for, I think we very much appreciate, that you're taking time to discuss with us, general relativity, especially on this very special day of November 25. Okay, thank you. Bye-bye.
Thank you, bye-bye.
Thank you.
Thank you for all